Hello everyone, welcome to the class. Today we will learn about the techniques to design IIR filters. In this lecture we will study about the impulse invariant technique and we will dig deep into that technique using examples also. Let's start. Before we go to the actual design of the IIR filters, there is a question which can come in everybody's mind that if there are two types of filters, FIR filter and IIR filter, then what filter to choose for a particular application? Let's discuss a little bit about this issue and then we will go to the design of IIR filters. This is a table showing the comparison corresponding to the FIR filters. We know that system function contain only zeros that we have already seen in the transfer function, and IIR filters contain both poles and zeros normally. FIR filters are non-recursive and recursive structures are both possible, but at present let us concentrate on the fact that FIR filters are non-recursive type of structures. Whereas IIR filters are recursive structure filters. The most widely used form is the cascade connection of first order and second order sections. We have already seen the various types of structures by which we can design the IIR filters involving direct form 1, direct form 2, parallel structures, canonic form, and cascade structures. Out of that, cascade structure is the most widely used type of structure to implement IIR filters. Now, FIR filters can have an exactly linear phase response. We know that FIR filters have linear phase response and the group delay is constant. That means all the frequencies while passing through that filter are delayed by the same amount. That is actually required in some high definition type of signals like music signal or video signal, right? The implication of this is that no phase distortion is introduced into the signal by the filter. Whereas the phase responses of IIR filters are nonlinear, especially at the band edges. So you cannot expect a linear phase response out of the IIR filters. The effects of using a limited number of bits to implement filters, such as round of noise and quantization errors, are much less severe in FIR than in IIR filters. But in the case of IIR filters, because of quantization means the number of bits that you select for the input and also for the coefficient values. So because of quantization of the filter coefficients, a pole can in principle move from a position inside the unit circle to a position outside the unit circle and hence cause instability. Actually, when you select the number of bits by which you will represent each coefficient, then if you consider less number of bits to represent coefficients, then in the case of IIR filters, the effect is that because of the selection of the less number of bits, the pole can move outside the unit circle and cause instability in the filter. Whereas this kind of problem is less in FIR filters, so you can choose a good amount, the reasonable amount of bits to represent the coefficients. FIR filters require more coefficients for sharp cutoff filters than IIR filters. Thus, for a given amplitude response specifications, more processing time and storage will be required for FIR implementation. So FIR for the same type of filter specifications, FIR filters require more coefficients and that will ultimately lead to more processing time and the storage capacity required. So FIR filters in that term, the hardware requirements are more, whereas IIR filters for the same filter specifications require fewer coefficients for sharp cutoff filters than FIR filters. Now, the complexity is proportional to the length of the impulse response. In the case of FIR filters, there is a direct relationship between the complexity and the length of the impulse. Length of the impulse response means the number of coefficients for which the moving average is taken. Now, no direct relationship between the complexity and the length of the impulse response. There is no direct relationship in the case of IIR filters. No direct relationship is there between the complexity and the length of the impulse response, which we know that it is in fact infinity in the ideal case. Filters with high selectivity can be realized with relatively low complexity. Now, FIR filters have no analog counterpart, whereas we know that IIR filters can be designed with the help of the already existing analog filters, and we can use those already existing analog filter transfer functions. We can convert those transfer functions into discrete domain, and then we can further apply the transformation to get the required response. Whereas in the case of FIR filter, there is no such counterpart available, analog counterpart available. So FIR design procedures are normally iterative procedures, and design equations do not exist. So it requires a little effort to design the FIR filters, whereas in the case of, but of course they are stable and they have linear phase. Whereas the analog filters can be readily transformed into equivalent IIR digital filters meeting similar specifications. IIR filters can be designed using design formula which already exists. We have to just make the transformation and we can get the desired response. But in this lecture, we will look at the design of IIR filters, one of the techniques of design of IIR filters, impulse invariant technique. Now, IIR filter design. In transforming an analog filter to digital filter, we must obtain either Hz or Hn. Either we must obtain the transfer function in the Z domain or in the time domain in the form of a difference equation from the analog filter design. In such transformations, we generally require that the essential properties of the analog frequency response be preserved in the frequency response of the resulting digital filter. So once we are applying the transformation, it should not happen that once we are transforming from analog domain to the digital domain, we must be able to preserve the frequency response required. Whatever is there in the analog domain must be there in the digital domain. This implies that we want the imaginary axis of the S-plane to map into the unit circle of Z-plane, because digital circuits will be explained through the Z-plane, whereas the analog filters will be explained through the S-plane. So there has to be the imaginary axis of this S-plane, because the left side of the S-plane we say that is for stability, and inside the unit circle is for stability of the filter in the digital domain. So therefore, we want the imaginary axis of the S-plane to map into the unit circle inside the unit circle of the Z-plane, so that the stability requirements are maintained. A second condition is that a stable analog filter should be transformed to a stable digital filter. That is, if the analog system has two poles only in the left half S-plane, then the digital filter must have poles inside the unit circle. This is in continuation to the previous point. If the two poles are there of an analog filter which lie on the left side of the S-plane, therefore those two poles must be transformed into digital domain inside the unit circle so that the system remains stable. Right. So consider keeping these conditions in mind, we must be able to design the digital filter from the uh, analog analog function, transfer function, by applying the transformation. Let's see how we can do that. Now, first technique that we will do for this IIR filter design is impulse invariant method. Now, in this method, we start from an analog filter. Of course, we start from the analog filter impulse response or the system function. Now, impulse response of the analog filter will be denoted by HAT, and the system function in the S domain will be denoted by HAS. Now, if the impulse response is directly given, then there is no problem. If the system function is given in S domain, then we must apply the inverse Laplace transform to get the signal in the impulse response of the system, right? So that means, let us assume that now we have HAT. From this HAT, we have to get HN now, which is the discrete form of this signal after sampling. Now, how can we achieve that? We have to replace this T with N and capital T, where capital T is the sampling frequency. So therefore, the objective of our design is to realize an IIR filter with an impulse response Hn, which satisfies Hn is equal to, so that means T is being replaced with N capital T. The characteristic property preserved by this transformation is that the impulse response, this is very important in the case of impulse invariant method. Please remember that the impulse response of the resulting digital filter is a sampled version of the impulse response of the analog filter. Right? We know this fact once we replace this T with N capital T, so we get the sampled version. And the impulse response is preserved in the digital domain as is there in the analog, as is there for the analog filter, is exactly preserved in the discrete domain. Let's see. Now, this first figure shows that it's the impulse response of the analog filter. And once we convert this impulse response in the analog domain to the digital domain by replacing small t with n into capital T, we can represent hn into capital T as hn also for simplification, for simplicity. Then we will see that the impulse response shape is exactly the same as the impulse response of the analog filter is exactly the same as the impulse response of the discrete filter. So therefore, the impulse response is preserved when we transform the filter in the analog domain to the digital domain. But let's look at the frequency response. And this is the frequency response in the analog domain. The capital omega is the analog frequency. Now this frequency, this point is analog frequency. In terms of analog frequency, it is minus pi by t, and this point is pi by capital T, right? This basically corresponds to half the sampling frequency, and this minus fs by 2, and this corresponds to half the sampling frequency, that means plus fs by 2. Now, and in the, I have also drawn the digital frequency axis also. This fs minus fs by t in digital domain actually corresponds to minus pi, and fs by 2, which is pi by 2 in the analog domain, corresponds to pi in the digital domain. So these things we must keep in mind. Now we see that this is the frequency response of the filter in the analog domain, and we know that the frequency response from minus pi to pi uh, in the digital domain will be exactly the same as the frequency response of the analog filter, but this response will repeat at periods of 2 pi. So one, and beyond this minus pi by capital T, if you go, the same spectrum in the analog domain will repeat in the digital counterpart. And when the sampling frequency is not very large, you will see that the two spectra will overlap with each other, and that will lead to aliasing, which means that in the impulse invariant method of transforming of designing IIR filters, this method suffers from the problem of aliasing. Though impulse response is exactly the same in the digital domain as in the analog domain, but the frequency response is not the same. It suffers from the problem of aliasing, right? We see that with this method, there are problems to a greater or lesser extent depending on the choice of capital T, because choice of capital T, which is sampling period, actually determines the sampling frequency. Now, if the sampling frequency is higher, then we can minimize this aliasing, because if you take the sample, if you take this graph more towards the left, so that means this will fall down towards zero. That means we can reduce the amount of sampling if we increase the frequency, sampling frequency. But even then, this technique suffers from the problem of aliasing. But important point is that impulse response remains the same. The sampling frequency affects the frequency response of the impulse invariant discrete filter. A sufficient high sampling frequency is necessary for the frequency response to be close to that of the equivalent analog filter. So it has to be high if you want the exact replica of the analog filter frequency response. Thus, due to aliasing, the frequency response of the digital filter will not be identical to that of the analog filter. So how do we find the filter coefficients of the IIR filter in this design method? Now let us take an example and see what kind of mapping is there in the inverse invariant method. Now if you look at this transfer function, the given transfer function is of a low pass filter. In the S domain, it is 1 over S plus B, right? So we need to first get uh, the impulse response in the time domain of the analog filter, right? So what we will do, we will take the inverse Laplace transform here, and we get HAT equal to e to the power minus bt, which is the impulse response in the time domain, right, using this inverse Laplace transform. So we get now the impulse response in terms of t. Now we know that to convert into digital form from here, we need to replace this t, small t, with n capital T, which actually corresponds to the process of sampling. Now we get HA and T equal to, and this T is also replaced, e to the power B minus B n capital T. Now this is HANT is usually written as HN. So we can express that e to the power minus BNT for n greater than equal to 0 is this thing, and 0 for n less than 0. And from here, this is the discrete time domain function, and we apply the Z transform here, and we convert the equivalent digital transfer function as 1 over 1 minus e to the power minus bt z to the power minus 1, right? This is the, because this is a single pole filter, right? In that case, you need to have only one coefficient. So this is basically the coefficient. E to the power minus b capital T is the coefficient of the filter. The mapping is very clear. The mapping is, you will be given with this transfer function in S domain. You need to apply the inverse Laplace transform to get the impulse response in the time domain. Then you get the sampled sequence by replacing t, small t, with n into capital T. And after that you need to take the Z transform, and finally you will get the digital filter in the digital IIR filter in the Z transform form, Z domain. Now it is seen that Hz is obtained from HAS by using the mapping relationship. Now this is the mapping. What is the mapping? The This is the HAS given. From there we will get 1 over 1 minus e to the power minus b capital T z to the power minus 1, as we have derived it here. So this is the mapping from the analog domain to the digital domain, where v is greater than 0 and capital T is the sampling period. So that means analog domain transformation to the digital domain transformation. That means S domain transformation to Z domain transformation. Now let's look at the what is happening in the impulse invariant method. Let us look through the mirror of S plane. In the S plane, along the x-axis is sigma, and along the y-axis is j omega. The imaginary axis corresponds to the analog frequency. Now this is minus pi by capital T, this is pi by capital T. So this strip of the analog spectrum, right, as is evident from here, from minus pi by capital T to pi by capital, this analog spectrum, that's what is we are trying to say here. This complete analog spectrum will be mapped to the inside of the unit circle in the Z plane, from minus pi by capital T to pi by capital T. But there are other strips also in the digital. Once we convert into the sampled form, there will be the spectrum ranging from pi by capital T to 3 pi by capital T. That strip will also be mapped inside the unit circle. Strip from minus pi by capital T to minus 3 pi by capital T will also be mapped into the inside of the unit circle. Now each strip maps into the interior of the unit circle, which actually leads to the problem of aliasing. The j omega axis is mapped into the unit circle of Z plane as shown in the previous slide. However, this mapping is not one-to-one mapping. Since small omega is unique over the range, this digital frequency is unique over the range minus pi to pi, the mapping small omega equal to capital omega into t, which that means this is the relationship between the digital frequency with the analog frequency, implies that the interval minus pi by capital T to pi by capital T in the analog corresponding to analog frequency is mapped to minus pi to pi in the digital frequency axis. Now furthermore, the frequency interval pi by capital T to 3 pi by capital T in the analog frequency domain also maps into the into this minus pi to pi digital frequency range. That's what I was trying to explain here. When the mapping, when I say that each strip maps into the interior of the unit circle, exactly that's the same point is mentioned here. And in general, so does the interval. So in general, we can write that every strip corresponding to the j omega axis, the imaginary axis, will be mapped into the inside of the unit circle, where k is an integer. Thus, the mapping from the analog frequency capital omega to the frequency small omega in the digital domain is many to one. It's not one-to-one mapping is there in impulse invariant method. It is many to one, which simply reflects the effects of aliasing due to sampling. So that's a problem with the impulse invariant method. But the advantage of that's what is again I'm trying to show here. These strips will be mapped inside the unit circle, which lead to the problem of aliasing. Right, but one of the advantages of this impulse invariant technique is that the impulse response is exactly the same as the analog counterpart, right? But the frequency response leads to the problems of aliasing once we convert an analog spectrum into digital spectrum. Okay, so we must keep the advantage and the disadvantage in mind. All right, let's take an example where we will try to design a digital filter from the transfer function given in S domain. Now, this is a second order transfer function given. Hs is equal to 2 over s plus 1 into s plus 3. Now, we know that we have to use this mapping. Please remember this. 1 over s plus b transforms to 1 over 1 minus e to the power minus bt z to the power minus 1. We have to use this transform. Therefore, we need to convert this into the form that I have just shown to you. So therefore, what I will do is I will take the partial using the partial fractions. I can segregate these two denominator factors in these terms, right? Using the partial fraction. So it will be, so we know, I assume that we know the partial fraction, how to get the partial fraction. And after solving it, we will get this equation 1 over s plus 1 minus 1 over s plus 3. Now we can apply the transformation transformation for converting from analog domain to the digital domain. So it is 1 over s plus b transforms to 1 over e to the power minus b capital T z to the power minus 1. So uh, here my b is 1, right? So what we will do is b is 1. So in that case, the hz will be 1 over 1 minus e to the power minus capital T, because b is 1, b will not come here. Z to the power minus 1. This is for the first term, and minus 1 over 1 minus e to the power minus 3t, because b is 3 here, z to the power minus 1. Now we take the LCM and we try to solve it further. We will be able to get this transfer function in Z domain. Okay, so that's the digital. So this is the transformation. This is the analog filter, and this is the equivalent digital filter. And this filter actually, what type of filter? In the if we try to analyze this filter little closely, what we are getting is, this is basically a naught. That means the coefficient of the numerator polynomial, and in the, if you look at the denominator, this is 1 minus b1 z to the power minus 1. What is b1? E to the power minus t minus e to the power minus 3 t. This is the first coefficient of the denominator polynomial, and e to the power minus 4t is the second coefficient of the denominator polynomial. So all the three coefficients for the numerator also and for the denominator also we have been able to calculate. So therefore we have converted the analog filter to the digital filter using the impulse invariant method. Let's try to look at one more example. Use the impulse invariant method to design digital filter from an analog prototype that has a system function. Now the analog filter has this transfer function s plus a, so it has a 0 also. Now to design a filter using the impulse invariant method, the standard procedure, we know that once we need to design the digital filter from the analog counterpart, we need to put it in the form so that we can apply the transformation from analog to digital domain. So in that case, you will have to use the partial fractions. So if you use the partial fractions and apply some little bit of mathematical manipulation, you will be able to say a over I mean, how have you come to this? How have you come from s plus a whole square plus b square to this point? So this is a if you look at the denominator polynomial, this is a quadratic equation. So from the quadratic equation, putting it equal the characteristic putting characteristic equation equal to 0, so we will be able to find out the roots. So two roots are found from here. One is a plus jb, and the other is, it will be minus sign out, minus of a plus jb, because that's how this negative has become plus. So the root which we have found is minus of a plus jb and minus of a minus jb. So two roots are found, so we can write the denominator polynomial like this. Now we can apply the partial fractions to get our desired form in the analog domain, so that we can make the transformation into the digital domain. After applying the partial fractions, the values of the a and b constants will come out to be half. So these are the this is the final result which we have got after doing the partial fractions, and we can take this half out and take this half out. So we will be able to 1 over s plus, this is actually, if you remember, this is very similar to this kind of transformation, that 1 over s plus b, that we try to apply while converting the analog filter to the digital filter. So two parts of the transfer function are there on which we can apply the transformation. Now if you apply this transformation, so in the first case the coefficient is a plus jb, so that's what we get, e to the power minus a plus jb. And for the second component of the transfer function, we get the same. So if you solve it further, right, so you will be able to get the final form of the transfer function, 1 minus e to the power minus a t cos b capital T z to the power minus 1 into the numerator side, and this is your denominator side. So that means you have been able to design, you have been able to convert the analog filter to the digital filter using the impulse invariant transform. This is the impulse invariant transform. And the derivation of this transform we saw here. How did we get the transformation? If the analog filter looks like this, we were able to get the equivalent digital filter transfer function in Z domain like this. Right. So this is a tutorial example that I am giving to you. The solution you will have to solve of your own. But the this is a second order Butterworth filter. The denominator side is the Butterworth polynomial. This filter is the normalized filter, right? Because you directly see one here, so that means it is a normalized filter. And assume that the 3 dB cutoff frequency of the digital filter is 150 hertz. So that means the cutoff frequency is 150 hertz and the sampling frequency is 1.28 kilohertz. So you will have to solve this example yourself. This is the frequency response in the digital domain, right? H of omega, such a and right. This is the DC gain you have calculated, which is 1223. Such this is the final expression. Excuse me. This is the final expression that you will be able to achieve or calculate after applying the impulse invariant. So you just try to solve this example of your own, and you can raise questions anytime you want. Thank you.